In this video we're going to look at the converse of Pythagoras. So this is the next lesson for the topic of Pythagoras' theorem. So the converse of Pythagoras. Now the word converse you may or may not have heard of out of the context of a pair of trainers, but the converse of a statement means swapping the hypothesis and the conclusion. Now, I know there's still hypotheses you might not have heard of again, so let's look at some examples and hopefully you'll understand what I mean. So if we've got this statement, if it is raining, then the grass is wet. The converse of that statement would be, if the grass is wet, then it is raining. So it's almost swapping the two things around in the sentence. If a polygon has three sides, then it is a triangle. If a polygon is a triangle, then it must have three sides. And I suppose to look now at what we're actually doing, if a triangle is right angled, then the square of the hypotenuse is equal to the sum of the squares of the other two sides. And if the hypotenuse squared is equal to the sum of the squares of the other two sides, then the triangle must be right angled. Now a converse in maths as well is also a type of proof, which you probably won't really meet again until you do advanced higher in 6th year. So this is quite different from what you've done before. So the working's quite specific. So let's look at that, and I don't want you to deviate from the working in this instance. I don't ever tell you that really, but in this instance do not deviate from what I'm going to tell you. So we know this already. We've met Pythagoras' theorem, we know the hypotenuse is across from the right angle, and we know that the square of the hypotenuse is equal to the sum of the squares of the other two sides. So let's see how this fits into converse of Pythagoras. We'll look at an example. So the sides of a triangle are of length 4.5 centimetres, 7.5 centimetres and 6 centimetres. Is the triangle right angled? Now at this point we've got no idea what the triangle might look like, but given that we are studying Pythagoras' theorem and it's all about right angled triangles, maybe we should apply this to a right angled triangle. Now we know that our hypotenuse, or where our hypotenuse would normally be positioned across from the right angle, so that would be here if we assume that that is a right angle. That's the longest side, so that has to be 7.5 centimetres, which means the other two sides are 6 centimetres and 4.5 centimetres. Now I realise the diagram's not to scale at all, which you should probably be able to see from this, but that's okay. We're just trying to get a visual picture in our head just now of what's actually going on. So if we look at our hypotenuse first, or what would be our hypotenuse if this triangle was right angled, and if we square our hypotenuse, so square the 7.5, and that gives us 56.25. Now let's examine what happens with the other two lengths. So if we square both of these and then add them together, because that's what the formula for Pythagoras would normally say for the two shorter sides. So we've got 6 squared plus 4.5 squared, and that gives us 56.25. Now hopefully you're thinking to yourself at the moment, well, those are the same. And that's good in this instance, because what it tells us is that if those are the same and those are equal, then this triangle must be right angled. Now for our answer we can't just say yes it's right angled and we're done. We absolutely can't do that. So we need to take our 7.5 squared and our 6 squared plus 4.5 squared, and we need to compare those. So we do know that they're equal because we got the same answer for each calculation. So we say in our answer, since 7.5 squared is equal to 6 squared plus 4.5 squared, the triangle is right angled. So we've got a few things here going on. We've done our calculations separately. That's very important for Converse of Pythagoras because, like I said, it's a proof. So we can't have these equal to each other just yet. We have a numerical comparison in our answers, and then we have to state whether the triangle is right angled or not. So just now would be a good time to pause the video and take this down in your notes jotter. Okay, so hopefully you've copied that down. Let's have a look at the second example, which is one in context this time. So a set square must have a perfect right angle at one of its corners. Does the set square shown have a perfect right angle? So we can see we've got a set square here, we've got this triangle, it's got the three sides and they're all joined at the corners. We can see, I suppose, where your hypotenuse might be if this was right angled would be the 14.5, and our other two sides 11.2 and 8.8. So let's take what would be our hypotenuse and square it. So 14.5 squared gives us 210.25. The other two sides is going to be 11.2 squared plus 8.8 squared, and that gives us 202.88. Now hopefully you're realising at this point that these are not equal to each other. The two calculations we have done have different answers. So we need a numerical comparison again. The square of what we were thinking was our hypotenuse is not equal to the sum of the squares of the other two sides in this triangle. So we need to say since 14.5 squared is not equal to 11.2 squared plus 8.8 squared, the triangle is not right angled. Therefore, the set square does not have a perfect right angle. Because we have to refer this back to the question here. It asked us about a set square, it asked us very specifically about an item, so we need to refer back to that. So if we just have a wee look at all of our working, we had separate calculations, we had a numerical comparison, we had to state whether the triangle was right angled or not, and finally we had to refer back to the question because it was a question in context. So just now would be a good time. We're at the end of the video anyway, so if you pause this just before the screen goes blank, and you can copy this example down in your notes jotter as well.